Guys, welcome back. We're just gonna jump right in. This is exactly where we left off before Thanksgiving break, and we're gonna finish up the kidney today. And it made it really easy for the distal convoluted tubule. Review the effects of aldosterone. Aldosterone affects the distal tubule. And if you recall what you learned from this figure, it's been presented before in endocrine. Facilitates sodium ion reabsorption. Specifically from the DCT. And then what I had said earlier was water follows, and that will increase blood volume and blood pressure. And this is really the only thing that you really need to understand for the DCT. By the time the filtrate reaches the end of the nephron, the DCT, there's nothing much left to reabsorb, just a little bit of salt and water. And so if the body needs these fluids and electrolytes, then aldosterone should be in the bloodstream. And that's what's shown here. It's a steroid hormone, so it can go right through the cell membrane and bind its membrane in the cytoplasm. And this shows the steps of making new channels and new pumps, and increasing the activity of existing channels and pumps to facilitate more sodium reabsorption. And then the filtrate will then empty into the collecting duct. And the collecting duct is receiving filtrate from many nephrons. Collecting ducts receive filtrate from many nephrons. And the main modification here is to form concentrated or dilute urine. That's one thing we'll talk about. Can form concentrated or dilute urine. So what happens is concentrated urine, well, it's obviously by the color, it's more concentrated, but the volume that's produced is much less. Dilute urine, in addition to being dilute, you're increasing the urine output. All right, and the other function of the collecting duct is, well, if you recall, acid-base balance. We'll revisit that again. And so you have two different cell types for these two different functions. For the first function, most of the cells of the collecting duct have the aquaporins, and that allow them to concentrate the urine, or if they're not using the aquaporins in those cells, that's dilute urine. And so that's kind of what I have here. I have a picture of the collecting duct and water leaving. Because if ADH is present, that'll mobilize those aquaporins. So the names of the cells that contain the aquaporins, well, they just call them the principal cell. So the principal cell of the collecting duct, they're the ones that have the aquaporins. And that's shown here. AQP is my abbreviation for aquaporins. What we had learned is that ADH can mobilize the aquaporins. It has to bind its receptor on the cell membrane to increase the second messenger signal. And then the storage vesicles which contain them, they won't remain in the center of the cell. They'll mobilize and insert the aquaporin on the filtrate side. So that way, by rules of osmosis, water will follow its osmotic gradient to be reabsorbed back into the bloodstream. Okay, that's what we had learned prior. This figure should look vaguely remote to you. I did present both ADH and aldosterone together in the endocrine chapter. All right, so this information is new though. All right, but before I erase this, the cells that do the acid-base balance are called the intercalated cells. Okay. Well, let's stick to this first function here, the formation of concentrated or dilute urine. And so you can kind of look at both left and right there. So what I do is I put the physiological range of what the kidneys are capable of doing. You know, these numbers are from the med physiology books. Well, on the one end, to form dilute urine, the kidneys can output 6 liters a day at a concentration of about 100. 100 millismolarity, 6 liters per day. On the other end of the spectrum, with high amounts of aquaporins, if you're dehydrated, say, concentrated urine. (1200 millismolarity). And that's about 0.5 liters per day. So that's the range, and let's just remember the physiological state. You form dilute urine when you're, say, well hydrated or overhydrated. Overhydrated. What's going on in your brain? You have osmoreceptors. And then when they detect low osmolarity in the bloodstream, it's like, okay, you got plenty of blood volume. Let's increase the urine output. So overhydrated means no ADH, decreased aquaporins. You know, in the collecting duct, right? That's what we're talking about here. And so the picture shows you that the collecting duct cells, it's pretty watertight. Here's my pointer here. So that the collecting duct is receiving filtrate from the DCT. There's the concentration there. So that value 100 just goes all the way through, and water is not reabsorbed. And so you're increasing the urine output. However, in a dehydrated state, when you have max ADH output, the aquaporins are increased, so you're reabsorbing water along the way, concentrating the filtrate as high as 1200. So this condition, dehydrated, the body's response to help conserve fluids, increase ADH secretion, increase aquaporins, you know, like I showed you in the figure, they're mobilized and they insert into the filtrate side of the cell and facilitates water reabsorption. So you don't lose it to the urine. Now I put the word urea here. One of the things that concentrates the medulla is, it's called urea recycling. So let me put that on this side of the board. Urea recycling helps reinforce the osmotic gradient. one of the things that's not really well, they do show urea kind of leaving there. What's happening is, I kind of outlined urea recycling on this slide. It's not hard to understand. When urea is in the filtrate and goes up to the cortical region, it'll stay in the filtrate because there's no diffusion gradient there. But when it gets into a very salt-heavy medium, it tends to leave the tubule structure and go into the interstitium and create this urea pool. But some of the urea will actually re-enter the ascending limb of the loop of Henle. It'll just kind of keep going around and around. It'll keep leaving here. Some will enter and some will leave, and it kind of pools here to help pull water out when aquaporins are present. So that's what we refer to as the urea recycling. All right, so to change gears about the collecting ducts, again, the principal cells have the aquaporins, therefore water and sodium balance, but few and far between, you have the intercalated cells, two different types, type A and B, therefore the acid-base balance. And so this kind of shows you the function there, but I think it's better just to look at the picture here. The type A, type B, intercalated cells for acid-base balance. So I got A there, B here. So just to break it down, what they're showing you there, you got a cell with filtrate over here. And you got blood on this side. And it depends how you, I guess, arrange the furniture. On this side of the room, they got the proton pumps. On this side, they have the bicarbonate pumps. Okay. Let me draw this a little more square. So if you're pumping out the hydrogen ions or protons on that side, and you're reabsorbing the bicarb on this side, how is that going to affect the pH of the blood? This is a good review for the acid-base balance. Will it go up or down if this is the physiology the cell is doing? Excrete, reabsorb base. Should increase, right? Increase the pH. And when would you want to do this? If pH is getting too high or too low? If pH is getting too low, this would compensate for that. So this is called the renal compensation for acidosis. And the other way is we'll just flip them. Just make it so the intercalated cell, you reabsorb the hydrogen ions in the blood, and you excrete the base. So that's what they're showing you with this cell. That's the type B. And so, I mean, the effect of pH in the blood would be to drop it, and that would be a compensation for if the pH is getting too high. It's called alkalosis. So this will be a renal compensation for alkalosis. So if I show you any cell, and you can figure out which side's the filtrate, which side's the blood, well, you should be able to answer that question. Is that cell of A or B? It's a B. You're excreting the base. Okay. So those are the intercalated cells. They work one way or the other. And we'll get back to acid-base balance. I do want to kind of end with that. We'll talk about some clinical cases of using blood values to kind of smooth a cause of an acid-base imbalance. All right, but anyways, so we're pretty much done with the nephron. Once you've finished modifying the filtrate, you have your urine, and I want to start talking about the rest of the urinary system, talking about the bladder reflex. So here's kind of the rest of it. After the kidney, you got the ureters that go down to the bladder, and then there's the urethra. So there's male and there's female. We talked about urethra before in repro. So the anatomy is not too much. What you're looking at here, ureters descend retroperitoneal down to the urinary bladder. I should specifically say to base of bladder. They illustrate the bladder cut open here. So what you're looking at there, you have a ureter. It's way up here, and it's going to descend. It's going to go to the base of the bladder. Maybe open up right there, and you got one from the other side. And what you see at the base of the bladder is this triangular shape, trigone shape structure. And they simply call it bladder trigone or trigone of bladder because it's like a triangle. Bladder trigone at the base of the bladder. The 3 points of the triangle, 2 are created by these orifices of the ureters. So the corners of trigone. So 2 are ureteric orifices. That's where the ureters dump the urine into the bladder. That was clear. Here and here. Now, the way it's illustrated, these ureters, they have to pierce the bladder wall. And when they do it, they don't drill a hole straight through. They kind of drill a hole at an angle. And that's very important to understand. So that helps prevent backwash of urine up to the kidneys, which can happen. But normally, when the ureters pierce the wall, ureters pierce at an oblique angle to help prevent, urine reversing its flow. They call that retrograde flow, backwards flow of urine to the kidney. Backwards to kidney. I mean, if you have like a wall you're trying to pierce and you go straight through, there's nothing to prevent liquid from going reverse, because as the bladder wall stretches, that opening will actually get bigger. But if you have a wall and you pierce at an oblique angle, as the bladder wall stretches, it'll pinch that shut. So that's the goal here, because your bladder is filling with urine, and that stretches the bladder wall, and it gives you the sensation of, I gotta go, right? And then so by doing that, you pinch that shut. That's what I'm trying to say. Okay, well, the third point of the bladder trigone is created by this orifice of the internal urethral sphincter. So what I should mention about that is the bladder wall has smooth muscle, and it's called detrusor. I'm going to color this in kind of reddish to symbolize smooth muscle. Detrusor. It's smooth muscle. It's the muscle of the bladder wall that helps you empty your bladder when you urinate. Something that's taught in 430 is the epithelial lining of most of the urinary tract is a transitional epithelium, and you should still know that. I mean, it's not shown anywhere here, but let me just write that on the board because you're supposed to know that. Transitional ET lines, urinary tract. Okay, simple side note reminder. The transitional ET has an ability to stretch and distend. Well, as the detrusor muscle, as it approaches the base of the bladder, the muscle fibers of detrusor, they form an internal sphincter, what's called the internal urethral sphincter. It's illustrated right there, you can barely see it. Well, let me just illustrate it by drawing circular fibers surrounding this proximal part of the urethra. Internal urethral sphincter. It's smooth muscle that it'll keep it shut, okay? It won't let the urine that the bladder stores from dribbling out. That's called incontinence. So when it's stimulated to be contracted, sphincters, they kind of like squeeze and it'll keep the urethra shut. So this tube right here is urethra, not to be confused with ureter. Right? You got ureter and you got urethra. Okay. So the sphincter is the urethral sphincter. Keeps urine in bladder. That's an easy layman's term to put it. I mean, we call these the storage reflexes, so you don't wet your pants. Storage. In men, the internal sphincter contracts during ejaculation, so that way you don't get ejaculate up into the bladder. Contracts during ejaculation, keeps semen out of bladder. So that's smooth muscle, the internal sphincter. They also illustrate in the UG diaphragm the external urethral sphincter. Okay, I don't know if you remember studying the UG diaphragm. Remember the deep transverse perineal and repro? Well, one and the same, but within that is the external sphincter. And also you see the vulvourethral gland there too, but we're not concerned with that now. So let me just draw another set of fibers going around there. So that'll symbolize the external urethral sphincter. Anatomically, you should already know this, within UG diaphragm. Now, like the, well, it's not smooth muscle, it's voluntary muscle, it's skeletal muscle. Okay. So this one you can, with conscious effort, tell yourself to hold it in when you got a full bladder and you're waiting to get to the bathroom. So as your bladder fills and you have continence, this little bladder trigone, and I've seen our milk, it's like a little water slide. And there's all these little grooves that point downwards. Okay, and it's like, but if the sphincters are shut, because you're in your storage reflex mode, it's not time to void your bladder yet, the bladder fills up from the bottom up, okay, which is, good design, right? The holes aren't up here, right? Otherwise you kind of like feel raindrops falling, right, in your bladder. But it doesn't. It kind of slides down and you start to fill up. So imagine you have a filling bladder there. And let me erase this. You'll start to feel the urge to go at around 200 ml. Quote unquote feel urge to void bladder. Excuse me. So they call these the feeling, these afferent volleys. Okay. And as your bladder fills up more and more and more, the afferent volleys, they increase in frequency and duration, right? Just the urge to go gets stronger, and you know what that feels like. I'll just say increase in strength and frequency. Most textbooks say that the max limit is something like 1,000 ml. I mean, at that point, you're going to be walking to the bathroom like this. It's probably going to be pretty painful. Yeah, that's 2 water bottles, right? That's about the capacity. You can see that when the bladder is empty, it has rugae. Just like the stomach has rugae. That just means folds. But as it fills up, it stretches out, and it has a capacity of about 1 liter of fluid. Okay. Let's see. So yeah, that's about it for the anatomy part. Let's remember that the female urethra, the male is about 8 inches, 6 to 8 inches, just a couple few inches for the female urethra, making females more prone to UTIs, urinary tract infections, simply because the bacteria has a shorter distance to travel to infect the bladder and the urinary tract. What I want to focus on is those bladder reflexes. And that will involve you learning some nerves that cause the bladder reflexes to hold it in or to void your bladder. It's called micturition. These bladder reflexes. So I'm going to erase this now. I just want to begin by reviewing the nerves you have to know for these bladder reflexes, just the ones we're concerned with here. And so there's afferent and efferent in the nervous system. And the afferent division, let's remember that all afferent nerves, the neurons have that unipolar design where, well, they kind of look like that. And, well, we're going to talk about pelvic nerves, right, as they're carrying the afferent signals, you know, the feelings that you realize you have a full bladder. Pelvic nerves. And for the efferent division, there's somatic and autonomic. Somatic nerves, cell bodies in the ventral horn of the spinal cord, gray matter, and they have these long, this multipolar design, and they have one long extension. They go in the nerve fibers. Now the autonomic nervous system, well, let me mention the somatic nerve you gotta know. Pudendal nerve, know that one. Pudendal nerve. So the autonomic nervous system, they have pre and post ganglionic fibers, and they have that structure where you have a preganglionic and the synapses to post ganglionic. That's kind of what we taught you in the autonomics. And the sympathetic division, SYM, the nerves we'll talk about are the hypogastric nerves. Hypogastric. Turns out the sympathetic nerves, they help you hold it in. Therefore, the storage reflexes. Hold it in. I think you know what that means. The parasympathetic helps you void your bladder, and those nerves are the pelvic splanchnic nerves. Parasympathetic, pelvic splanchnic nerves. They help you void. So keep those nerves, the names of them, in your head as you study this figure. And we'll study both reflexes to help hold it in. The storage reflexes, or micturition, which is to void your bladder. And what they do is they show you the essential parts of the nervous system you have to know on this figure. Up at the top you have the brainstem, the pons. And then they do show you a thoracic, or sacral spinal cord, because let's remember that the sympathetic nerves emanate from thoracic or lumbar regions, and that for the sacral region, that's usually where you have parasympathetic function. Okay, so that's why we're showing you each part there. Brainstem for command, sympathetic, parasympathetic function. So we'll do hold it in first. Storage reflexes. This is usually you're not conscious about it. Okay, I mean, maybe you can feel your bladder is full, but you don't really put in effort to hold it in unless you really, really got to go. Okay, but you have reflexes that help keep the urine in the bladder, so you don't have to like use brain input. There's something called the somatic loop that's very effective at keeping urine stored in the bladder until it's an appropriate time to go. So here you have that blue nerve. I'm not going to map out everything here, but just to get the ball rolling. You have that blue nerve, right? That's our unipolar thing. And you see it going into the spinal cord there. And it's synapsing onto the pudendal nerve. When the pudendal nerve fires, it's going to keep that external urethral sphincter contracted. Okay. So it'll synapse onto pudendal. So this is the pelvic nerves I was telling you about. That's carrying the afferent signal. So the signal is, it's signaling that you have urine in the bladder, and it's synapsing directly onto this efferent nerve, which is pudendal. Which will contract external sphincter. That's what it's showing you there. So I'll put a plus sign, external sphincter. I don't want to draw the whole thing, but I at least wanted to draw this. They call this loop, where the afferent signal goes in, and then the efferent signal goes out to contract the external sphincter. They call that the somatic loop. Because it's a reflex, it goes in and out, it's a loop. It's a direct stimulation of pudendal nerve. A reflex that directly stimulates pudendal. So that'll help you hold it in. And what you can see from the figure is that this pudendal nerve can have dual input. If your bladder gets really full and it's effortful to hold it in, that's kind of when the brain can influence this whole thing. So what they show you is this line from the Pontine Storage Center. It's going to come in and it's going to doubly stimulate that nerve. That's the conscious effort part, right? So what we'll say is, I'll use a different color here. Right, this is like from the Pontine Storage Center. Pontine means pons, right? The region of the brainstem. Now, saying that brain can influence. So that's just you helping yourself hold it in because you got a really full bladder and you really have the urge to go. The other thing I haven't mentioned yet is the hypogastric nerves. It's not part of the somatic loop, but you should also see that there's another arm going up here, and it's stimulating the sympathetic hypogastric nerves to help you hold it in. So let me outline that for you. So pelvic nerves also stimulate hypogastric nerves. So I'll say that they're stimulated. And if you look at the figure, they do two things. They inhibit detrusor and they stimulate the internal sphincter. Inhibit detrusor, stimulate do? Number one, how do you hold it in? This reflex. The pelvic nerve, that's afferent to the pudendal nerve. That will stimulate the external sphincter. Okay? You can get help if you have a really full bladder. The brain can influence to reinforce this somatic loop. And the other thing is the hypogastric nerves. I didn't draw it here, but that's what they're showing you here. They put a negative sign right there. Negative means stimulate or inhibit. Inhibit. Positive means stimulate in that figure when you study it. This used to be from the Marriott book. They have since dropped it, but I still teach them. I think it's very an effective learning tool. Okay, so let's say, okay, you got a full bladder, you make it to the restroom, and it's time to go. Now you want to utilize the Pontine Micturition Center to help you avoid the bladder. So to avoid, I'll study the efferent effects of the Pontine Micturition Center. Study the efferent effects of the Pontine Micturition Center. So on this figure, they show you that you have an afferent signal going all the way up to the brain, telling you have a full bladder, it's time to go. And then so that, if you follow that stimulation down, there's three things that it kind of outlines for you. This first thing here is you have an efferent fiber that inhibits hypogastric. So if the phrase is you inhibit the inhibitory. Number one. Inhibit the inhibitory hypogastric nerves. Because they were keeping you from going. They were inhibiting the detrusor muscle and stimulating that sphincter. So you want to turn that off. Okay, they put a negative sign there. So that way you're not inhibiting the detrusor muscle. So the second thing is they go all the way down to here, and there's a nerve fiber that stimulates the pelvic splanchnic nerves. Those are stimulatory to the detrusor muscle. They'll also inhibit the internal sphincter. Number two, stimulate pelvic splanchnic nerves. Okay, those nerves will do two things. One, stimulate detrusor. I'll put a plus sign. Detrusor. I'll put a negative sign. You inhibit the internal urethral sphincter. But don't you have an external urethral sphincter? Yes, and so that's the third thing I'll list. They inhibit pudendal. And by doing that, you'll inhibit the external sphincter. Inhibit pudendal. By inhibiting pudendal, you inhibit the external urethral sphincter. That's a good exercise to get you to review how reflexes work, a little bit of a neurophys there. And I think the trouble that students usually have are just kind of trying to remember the names of the nerves, hypogastric, pelvic splanchnic. And there's a few times, and what I've written on the board is, I think, the essence of what I want you to know for those two reflexes. The final topic for a lecture is a bit of sleuthing. Put on your thinking caps. And what I'll do on the test is I'll give you 1 or 2 case studies in which you need to analyze blood values to determine the cause of acidosis or alkalosis. And it'll get you to consider both renal and respiratory systems, which are covered on the last test. And so what I've boiled it down to are 8 possible clinical diagnoses. And I want to give you the tools to figure out how you reach any one of these 8. So on an exam, I'll give you 2 or more. Usually it's a couple few. And it'll be one of these 8 scenarios there. And so how you arrive to the appropriate conclusion is to consider the 2 systems that can influence the pH of the blood, your lungs and your kidneys. Okay. So if the lungs are involved, we use the term respiratory. If the kidneys are involved, oddly enough, they use the term metabolic. I'm not sure why. All right, so for example, to go back to the respiratory, if you have a problem with the lungs and the respiratory system is a cause of an acid-base balance, here's what you should look for. First of all, understand what we're doing is we're using blood values to determine the cause of an acid-base imbalance. Okay. I'll define the blood values that you have to analyze, but first I just want to kind of review. I'm emphasizing respiratory metabolic. If it's a respiratory cause, maybe there's COPD, maybe there's cystic fibrosis, maybe there's a number of clinical things that may cause an acid-base balance that's either a respiratory alkalosis or acidosis. Which one is the pH is too high? Alkalosis or acidosis? pH too high, pH too low. Okay, that's something you have to keep straight. And I'm saying that the lungs are the cause, one way or the other. And you can tell that the one thing you want to look at is the partial pressure of CO2 in the blood. Look at PCO2. Remember that? We kind of talked about that in the gas exchange lecture for that unit exam. And, well, let's see here. The normal range is PCO2 25 to 45 millimeters of mercury. Okay. The other thing I should mention is the normal range for pH is 7.35, 7.45. Happens to be a coincidence that it's 35, 45, 7.35, 7.45, and it's just a coincidence there. And remember the normal ranges, because for example, if you have an abnormal pH, that's kind of what we're looking at here. I said alkalosis, acidosis. Now we can numerically define it. If it's alkalosis, it's going to be above that number. And if it's an acidosis, it's going to be less than that, okay? So for example, let's say pH is a little bit low, 7.2. And let's say, I'm just going to tell you, it's a respiratory cause. It's a respiratory acidosis. What you would expect to see if it's a respiratory cause is that the PCO2 is too high. Let's say above the normal range, say 46. That would acidify the blood. Okay, let's remember why. If you have too much CO2, I mean, what do you create when you combine it with water? Carbonic acid, H2CO3. Which is a weak acid which will partially dissociate. So you create a little bit more acid there. And so if you have too much of that product, you push the equation this way, creating more acid. Okay. So you have to remember your chemistry so that this makes sense. You're not just memorizing that, oh, high drives the pH down, which it does. Okay. So then the opposite is true, right? Let's say you observe a blood value of pH 7.6. Is that too high or too low for pH? It's too high. And let's just say the lungs are the cause. Let's say it's a respiratory alkalosis. The opposite is true. If pH is too high, PCO2 is too low, maybe, let's say 30. I just chose a value that was below the normal range. Okay, that's too low. So, I mean, the rules of chemistry is, if this is too low, you push the equation the other way. So you get rid of your acid, and that'll drive the pH up. Okay, so these are the things you have to keep in your mind when you try to make these types of analyses. And well, it's not that hard. I mean, one easy rule, if you like rules, is when that value is high, you observe that because that's low. So this is like, let me use a different color. If this value is high, that's the cause, and that's why you observe this to be low, and it's the vice versa. If that's high, it's because this one was low. So we say respiratory opposite, if it's a respiratory cause. Oppo. The other system you have to look at are the kidneys, because they can excrete acid or base. So first of all, before I erase this board, any questions on the respiratory cause? You look at the blood value, the PCO2. Okay. The renal cause metabolic alkalosis acidosis. And the blood value they typically look at is the base, bicarb. Look at the base value, HCO. The units are kind of weird. They use milliequivalents per liter. In the normal range, it usually falls 22 to 26 milliequivalents per liter. 22 to 26, that's your normal range. And you still consider the pH normal range 7.35, 7.45, okay? So let's say, as an example, the pH is 7.30. Is that too high or too low?
Too low.
That's too low. So let's say this is an example of a metabolic acidosis. So if the value you look at is the base, would base level causing an acidosis, would base be too low or base be too high? If you know it's causing an acidosis in the blood level. This is where your A in chemistry kicks in, right? Or your B. I'm telling you, this is going to drive the pH to be too acidic. Probably don't have enough of it. So let's say the value is 20. That make sense? For whatever reason, the renal mechanism, you're not reabsorbing bicarb, you're excreting too much base, for whatever reason. So basically, not enough base drives the pH down. So let's say the opposite is true. 7.48, okay. The pH is too high, so let's say the kidneys are the problem. You'd call that a metabolic alkalosis. All right, so where am I going with this? What would be the base value to cause the pH to be too high? The value should be, well, higher than 26, and that's kind of where I'm going with. Let's say 28. So the rule here, if you see a low pH, and it's a metabolic cause, you expect the base to be low, low, low. And if the pH is too high, and it's a metabolic cause, base is too high, high, high. So high, high, low, low. So they call that, the metabolic equal. That's kind of what I titled this slide, right? Because low equals low, high equals high, right? So Rome is the respiratory opposite, metabolic equal, just to help you kind of, muddle your way through this as you're learning it. All right, so the other thing that's kind of the kicker is, if one system is failing, let's say number 1 and number 2. Let's say the kidneys are not doing well for you in maintaining acid-base balance. The question you have to ask yourself is, are the lungs compensating? Or, the reverse is true. If the lungs are failing you, are the other organ systems helping you? Are the kidneys helping you? So that's the other thing you have to consider, okay? So just to kind of work through some of these problems, the best way to teach it is just to go through a few examples with you. Let's see, okay, yeah. And I follow, there's different ways to do it. I follow the one in the book. So maybe I should give you a page number to refer to if you prefer relearning yourself later if you don't quite get it right now. Chapter 26. Page 1034 in this book. That's what this lecture is based on. 1034. Oh, that's all right. So when you study this, the first thing you do is commit to memory the normal ranges that we just went through. Let me write them on the board. What was the normal range for pH? 735, 745. Okay. The normal range for PCO2? 3545 millimeters of mercury. And then 4 bicarb, and the units are milliequivalents per liter, 22 to 26. Okay. So what you do is just kind of stepwise, 1, 2, 3, consider each one, and then I guess as a fourth step, make your diagnosis. And so what I would have to do is give you those 1, 2, 3 values. So the blood test comes back. Let's say pH is 6.9, 29, 19, and I'll leave the 4 blank. We'll go through the thing together, and always remember your roam. That'll help you through as you solve problems. So let me do the first one with you. For example, 6.9, that's easy. Is that too high or too low? That's too low. Yeah. So immediately you can say, this is acidosis, right? I'll just write that in at the bottom. Then, is it a respiratory cause or a renal cause? Then you start looking at those values. Just for sake of just following the same procedure, look at PCO2 next. Is that high, low, or in the normal range? No, that's low, but is that the cause by being too low? What's the rule? It should be opposite. If that's low, that should be opposite if that's the cause. So all you say for right now is, this is not the cause. It's not within the normal range, but it's not the cause. And we'll come back to it, but let's move on. Number 3. Evaluate 19. High, low, or within the normal range? It's low. So what's our rule? Low, low. This is the cause. So we know that the acidosis is a metabolic acidosis, something's wrong with the kidneys. So the last thing you have to do for your diagnosis is, once you figure out what the cause was, circle it, what you want to do is ask yourself, is the other system compensating to try to correct that pH that's too out of whack? So let me tell you the simple rule. If it's not in the normal range, it's compensating. Okay, now let me explain the physiology why. Why would CO2 being too low help you? Because CO2 acidifies the blood. So if the lungs are breathing off more CO2 to get rid of it, it's trying to bring the pH back up. So this is a respiratory compensation. That will be the full correct answer. Metabolic acidosis with respiratory compensation. So before you ask any questions, let's do another one. Blood value 7.2, 36, 20. Yeah, let's do it again. 7.2, is that high or low? Low again. So what can we diagnose immediately? Acidosis. Okay, let's figure out what the cause is. Well, let's see. 36. Is that the cause? Well, that's in the normal range. That's not the cause. So you can evaluate the value of 20. Wait, that's low. Low, low. Okay, that's the cause. Huh. Oops. Yeah. Drop it. So this is the cause. I'm going to circle it. That's the cause. So this is a metabolic acidosis, is what I'm saying. So your kidneys are failing you. Are the lungs helping? Well, if it's in the normal range, the rule is they're not helping. Okay, so that's all you say. So this is a metabolic acidosis without the respiratory compensation. Okay, here's the next one. Okay, at this point, I did 2 of them. Are there any questions? Okay, let's see. Let me give you another one. 725, 48, 30. Okay, you do this one over the next minute and I'll check back. You can talk it over with your neighbor. Is there any brave soul that wants to volunteer their answer? Yeah.
Respiratory acidosis with renal compensation.
Respiratory acidosis. Did you say with?
With.
Renal comp. Let's check it out. Okay, so here's what I would do. Number 1, that value is too low. Definitely is acidosis. Okay, next value. Oh wait, that's high. High, low. Oh, too much CO2 that acidifies the blood. This is the cause. So respiratory acidosis checks out. Let's look at the third value. So we know what the cause is. We just ask yourself, are the kidneys compensating? See, that value is, it's outside the normal range. Let's think about this. Too much base. Won't that help correct that? Yes. Boom, that's right. Okay. Let's see here. 1, 2, 3. We're going to do one more for good measure. Running out of room on the board here. Let's see. 7.32, 46, 25, and go. All right, this one is 732. That value is low, so that's an acidosis. 46. That's high. So that's low, high, that's too much. So we know that it's a respiratory cause. Are the kidneys helping? No, because they're just within the normal range. So, without renal comp. Of these 4 examples, what did I not ever give you an example of? Alkalosis, okay? And so what I want to do is, I want to take a break, and when we come back from break, I'll give you more things to practice, but the number one thing you should get done is the kidney dissection. Now, let me explain to you how that's going to work before you, I send you off into the rain. You can find shelter somewhere. I got these like little half sheets, and these have all the structures I want you to find. 12 things. I want to make the lab 15 points just to find these 12 things. And well, everyone can have one of these, but really I'm only going to check off one, and you can just turn in one per group. And it's good to have an atlas or a picture of a slide to look at to help you find these 12 basic things. And these things are easy enough to just cut that kidney in half, lay it open like a book, and stick a pin in it. And I'll even give you like ink markers and lab tape so you can kind of like label your pin. So when I come check it out, I'm just looking at the 12 pins. And since you'll have 2 halves, you don't have to stick all 12 in one, unless like the other half really stinks for whatever reason or you don't want to use it. But if you have 2 nice ones, you know, you can use them both to stick them in. I'll have everything set up when you come back, and I'll give you some more examples, practice. So come back at, I'll say 9:15.